All right, so let's look at this one. This is the next sort of thing. So remember when we had an electron, it had a charge. We called that E. It also had a mass, we just learned, ME. It also has one other property, which is its magnetic moment. Actually, it's what's called the spin angular momentum, but that spin angular momentum gives it a magnetic moment. And it's completely unrelated to the charge, right? The electron has a radius of less than 10 to the minus 22 meters, right? It's more than a million times smaller than the radius of a nucleus. And we don't know how small it is. All we know is that, as far as we can tell, it's perfectly spherically symmetric, and it could be very well just a point in space. So we don't even know if the electron has a radius, but we do know that even if you took this radius and you took this guy spinning around like that, you'd have to get a magnetic moment this way from a current loop, like we talked about before, this electron charge would have to be spinning much faster than the speed of light. So this magnetic moment has to be unrelated to the spinning charge. So that's just to say that this magnetic moment on this electron is a completely different thing. And we saw, with respect to the magnetic field, let's say we had a magnetic field pointing up, that if you had a electron going at a speed v, then perpendicular to both of them, it would turn perpendicular to both of them, right? It would try to go away that way, just to circle around. We'll find in a lecture or two the magnetic field, but it just wants to go in a perpendicular direction. The magnetic field won't accelerate or won't change the speed of the electron, but it will make it turn. So that's what happens with with just a charge, right? But the electron also has this property of having a magnetic moment. The property of having a magnetic moment means that the field could interact with it in different ways, right? In fact, it can interact with it in two ways. One, part A, is going to be a torque. This torque is going to try to align this electron along the field direction. So here I've got a field that's going to be non-uniform, but the magnetic moment is going to try to stay in the direction of the magnetic moment, or try to point up, or magnetic field, excuse me. Magnetic moment tries to point in the direction of the magnetic field. And if it doesn't point that way, it'll have a torque around there. Actually, it will precess like this to try to get to this spot. Let's see what's going to happen to the force. Well, if this were a uniform field, then there'd be no force on this electron who's just sitting there in the field. You'd still have no force. Electron that's not moving in a uniform field will never start moving. It might start to precess, it might start rotating, but it won't start to move left or right or up or down or any other direction like that. And there is a way to look at this, right? Look at that force. If we were to look at this particular case here, if we were to say 0 is right here at the large pole cap, which has a 100 millitesla field right here, and we were to say 2 centimeters, we're going to call this 2 centimeters right here. That's 2 centimeters from 0. That's going to have a 200 millitesla field. It's going to be the smaller pole cap that has a larger field because there'll be more flux. Well, they have the same flux, and it has a smaller area. So with the same flux, smaller area, you're going to need a larger field. So at 0, you have 100 millitesla, and over here you have 200 millitesla. And then you have this straight line field between it. You'll see that where the electron is, which is 1/2 the way through at 1 centimeter, at this particular point, the field is 150 millitesla. And the force is going to be related to the slope of this line. Now, if you have a nice straight line like this, so that's going to be a gradient field, and that gradient is going to cause the force, is going to cause the magnetic moment to, let's see, go down, I think. It's going to follow this slope downwards, I believe. All right, so that's going to be the second part, but because we don't have the calculus to calculate the gradient, we'll use a little more complex a procedure. But the torque is actually fairly straightforward. The torque, as we said in the lecture, was, N equals B mb sine theta. Okay, where theta is going to be this angle here, which is 45 degrees. So that means we have to use the magnetic moment of the electron, which is 9.28, excuse me, times 10 to the minus 24, is it 24? 24, yeah, amps per meter, or amp meter squared. Not sure why I get that wrong. The field is this point right here in the center, which is 150 millitesla. So that's 150 times 10 to the minus 3 Tesla. And then sine of 45 is 1 over the square root of 2, or 0.707. Okay, so then we just multiply these numbers together. Let's see, how does that work out? Multiply them all together, you get 984. And then you have 10 to the minus 24 times 10 to the minus 3, so that's times 10 to the minus 27. Amps times meter squared times Tesla. This is going to have to be Newton meters. So you have 984 times 10 to the minus 27 Newton meters. That's fine, but how do we find the force? Well, thinking about it, I probably should have just only talked about this in a linearly decreasing field, but I didn't. So when I didn't give you a formula for that. Instead, what I said, we have to pretend that we have a magnetic dipole. So this is just a pretend dipole. And so when we do that, we pretend there's a little bar magnet here, and that at each end of the magnet, there's a charge. So down here, away from the arrow, there's a minus QM charge. Way up here, there's a plus QM charge. And then we have a force that looks like the force for a charge in an electric field, only in this case with a magnetic field. So we're going to have to find, that should be B minus, we're going to have to find that. So how are we going to find that? Well, we have to find both QM and these B's. And actually, we could just have 2QM times delta B. That's because, let's say we have B plus, that's going to be the value of B in the center, which was this 150 millitesla right here, at the actual point in the at the actual point where the electron is. So this is the actual spot of the electron. And then we say, okay, we're going to have a little bit of an extension here. So we said this was 2 centimeters here. We'll make this 2 millimeters. Probably a little bit large for this kind of approximation, but since it's a uniform field, actually doesn't matter. If it was a non-uniform field, or since it's linearly decreasing, it doesn't matter. If it was decreasing with a more complicated dependence, then we'd really want to use a much smaller size. So we add that b1/2. We add to that something related to the slope, which is delta B, which is the difference between 200 and 100, so that's 100 millitesla, over the slope was 2 centimeters, so that's the distance there, or let's not use that D, let's use L, the length of the distance here to here, times D, which is the distance from here to here, probably, right? And that is, the magnetic moment is going to be equal to that QM times the distance between the pole caps. So that's the same distance here and here. Okay, and in this case it's also going to be times cosine of theta, right? So if this was horizontal like this, cosine theta would be 90 degrees, and that means there'd be no difference between B plus and B minus, and so you'd have a totally compensated field, and you wouldn't get a force. But if it was directly aligned, then you'd have a distance D here. And actually that should probably be D over 2, because we want to go from the center here. Alright, so this is sort of what we have for this, and what we only care about is this term, right? This term, we want to come back in here. So I need to call it something different. I've got 2 good reasons to call something that. So for that part, you have the difference between these, which is 100 millitesla, over this distance, which is 2 centimeters, times 1/2 of the distance between the pole caps, which is 1 millimeter, times the cosine of 45 degrees, which is 1 over the square root of 2, which is 3.54 millitesla. So that's what we need for that part. And then we're going to use that with this over here. So we have to use this to find QM, which is going to be the magnetic moment over the distance. The magnetic moment we already said was 9.28 times 10 to the minus 27, or 24, right? Amps meters squared, all over the distance, which is 2 times 10 to the minus 3 meters, right? So that's in millimeters, so it's 2 millimeters from here to here, so along that entire side. So that means that's going to end up being 4.64 times 10 to the minus 21 amps, now times meters, because we cancel out one of those meters. And that's what the charge on a magnet, the fake magnetic charge, that's what the unit would be, right? Whereas for an electric charge, it would be amps times seconds to give you a coulomb. Okay, so that is what we get for the charge. Now I've made a mistake here, so this should be a 21, because this should be a 24. So, right, I'm supposed to use this number instead of mixing and matching. Okay, so now we've got these 2 numbers, we can find the net force, right? So we have QM times B1 minus QM minus B. So we have like I said before, QM times the delta B, and QM is 4.64 times 10 to the minus 21 amps times meters. Yeah, wait, this should be 2 delta B. So, and then we have 2 times this should be a 2, so this should be a 3.54. 3.54. So 3.54 centimeters, 2 times 3.54 millitesla. Excuse me. I'm sorry. It said it was changed. Maybe it didn't change it on this slide, and it'll come back on the next slide, I hope. Let's see. So we put all that together, and we end up with 32.8 times 10 to the minus 24 newtons. Okay, so we have a very small force on this. Now, remember when we were talking about the mass was times 10 for this guy. The mass is 9.11 times 10 to the minus 31 kilograms. So even though this has a small force, with 10 to the minus 31 kilograms, you divide this by this, and you end up with something on the order of 3 million, let's say 3 million newtons, so, or 3 million meters per second squared. So it's really a very large acceleration, even though it looks like it's going to be small because this is such a small number for the force. For this guy, you have a very small number for your torque, but I don't know if there's even a moment of inertia. So I don't know if anybody has an idea of what the moment of inertia of an electron is, or how to measure. So that's a good research question. If you want to, drop out of pre-med and turn into a physicist, is figure out how to measure the moment of inertia of an electron. Although that may be exactly what they're doing when they're figuring out how smooth the electron is. So they know that the electron is perfectly spherical, or is spherical down to an enormously small number, as well as being incredibly small. So they want the electron actually to be a little bit oblong because it tells you some things about the standard model of particle physics, but it doesn't quite work, or they can't get anything that isn't that way. So yeah, I didn't make that correction there. I just need to change that number, and unfortunately that number goes all the way through, right? But anyways, so the torque is fairly straightforward, and for the force I introduced this equation because it'll take you so long. It's the only way you can really, in general, figure out what the force from a field is on a magnetic moment in this course. Now, there's a way to do it with calculus that's really, really slick. And I guess looking at this for this special case, I could have produced an equation that was actually simpler than that. Actually, I did produce that equation for you. But it is for a special case, so it's not really that amazing as far as that special case is concerned. So this is a way you can figure out that force, but the distance d here, the fake dipole distance, has to be small, right? The fake distance between the charges has to be small. And so the only way you can figure out if it's small is if you keep reducing it, how much does the value change, right? And when you get to a point where the value changes say less than in 1 part in 100, you're probably close enough for whatever you're going to get to a reasonable approximation. So if you need to use it for that, which you won't, because if you need to do something like this, you'll be able to do the things that are more complicated, right? So anyways, this is the best we can do to figure out forces on dipoles in this class, and it works. It is approximate to a degree, but it works fairly well. All right, so I will talk to you next time. Bye now.